All right, let's work through some practice problems here. This is on vectors and projectiles. And so first of all, let's just review. We've done this before, but let's talk about it again. When we're talking about a vector, we're talking about something that has both magnitude and direction. Examples of vectors would be displacement. Now, displacement would be used, we usually talk about distance, but distance is a scalar. Velocity, acceleration, force. Those are very common ones that we use in science that are vector quantities. If we're talking about scalars, scalars only have magnitude. They would be distance, speed, mass, time, volume. Good examples of scalar quantities. When we talk about vectors, we use arrows to represent them. And we can place the arrows head to tail to see what our resultant vector would be. So if we've got a vector that's like this, and then we've got another one that's that, we can put them head to tail, and then my resultant vector, this is the same thing as that. It'd be the resultant vector. And we use that a lot. You cannot do that with scalars. You can do it with vectors, though, and that's how we work with a lot of vector quantities and figure some of these things out. Now, vectors don't have to be lined up in a straight line. In fact, a lot of times they're not. So, for instance, in this example, we've got this vector here, and then we put the next one head to tail. So the head of the one, tail of the next one. Here, my resultant vector is this. Now, that's a little different than what we've been talking about before. Before, we had always talked about the parallelogram rule. And you could do that with the parallelogram rule. You could still figure it out. You would do it just a little bit differently. You would do this, and then you would take this vector here, this one right here, and you would, see if I can do this. Maybe I can't do it with this ink. Yeah, I'll try it a different way. All right, so I would take this vector, and then this one, I'll try to just draw it about the same. And then I would draw the parallelogram, which is going to be this, and then the resultant is still the same thing. But sometimes it's just easier to say put them head to tail, and it works better. We can solve these both graphically, put it on graph paper, actually measure it out, take a ruler, measure it out. We can also figure it out with vector components. If we know the length, we know angles, we can do things with that. So for instance, let's say that we wanted to do it graphically. We could just do something this simple. We could say, well, here's my first vector, and I would measure that out, and maybe 3 squares on there on the graph would indicate that, and maybe this would be like 4 squares on my graph paper, and maybe that's 2 or whatever. And I would end up and put all those vectors head to tail, and then my resultant vector is this one right there. And so graphically, you could figure that out. And then if you wanted to figure out angles, you would take your protractor and you would actually measure that angle and figure that out. So if that's one way of doing it graphically, you can do that. More likely, we spend probably some time talking about angles and doing things in components. So let's take a look at this example here. If we know the resultant vector, so we know that. We know the resultant right there. We can break that down into its x components and its y components. So you can break it down, and you still got your triangle again. And notice that you've got head to tail, and you've created your triangle. Or if you didn't like that particular method, you could do it the way we've been doing it with the parallelogram idea. You've got this, you've got here, you've got here. Either one of them works. They're both really the same thing. And then you could figure that stuff out. If you knew this angle, you could figure out all of those sides using trigonometry, which we'll do here at the end here. All right, let's work through a couple of quick examples here. Every March, the Swallows return to Capistrano after their winter in the South. Let's say that they go 200 kilometers on the first day, 300 on the second day, 250 on the third day. Draw a vector diagram and find their total displacement. Now, displacement is simply the vector term for distance. So on the first one, we went 200, then we went 300, then we went 250. And since they're all in the same direction, that's pretty easy. We just add them all up and we get 750. So that's a pretty simple problem there. Now let's do it just a little bit more difficult. Let's say that here we're talking about this guy who's got such strong teeth that he can actually move a car. So let's say that the car was pulling forward with a force of 20,000 newtons, and he's going to apply a force of 25,000 in the opposite direction. So here's my car. It's going this way. Here's his force. It's going that way. What is the resultant? Well, the resultant is the difference here, which would be this much right there. So in other words, what we've done is we've gone this way. If I put it head to tail, I'm going back here, and I started at this point, so what's left is this right here. So that's my resultant vector in that example. All right. Now the next one talks about Barry Bonds and says, well, let's say, for instance, that he hits the baseball at a speed of 50 meters per second. There's a wind, at 90 degrees to that, blows north. So this wind is north. This is west. And we want to figure out, well, what's the actual speed of that ball? Because we've got 50, we've got 5 here. Well, think about this. What have you got here? You've got 2 parts of a right triangle. So you've got a right triangle, and 2 sides. You can certainly figure out the third one. That's just Pythagorean theorem. A squared plus b squared equals c squared. So plug in your numbers. 50, 5, square them. Take the square root of all that. You end up with 50.2, and it would be moving northwest. And we can figure out that exact angle if we want to by using tangent. Because we know that if we want to figure out this angle, tangent is going to be the opposite, which in this case is 5 over 50, or 0.1. And if we do our inverse tangent, we're going to end up with 5.71 degrees. So this angle would be 5.71 degrees. The resultant would be 50.2 meters per second. And that would be our answer there. Alrighty. So now we have the Maton family begins a vacation trip by driving 70 kilometers west. Maybe they're going to see the space shuttle or something. I don't know. 70 kilometers west, then they drive 700 kilometers west, then 600 kilometers south, 300 kilometers east, and 400 north. Where will they end up in relationship to their starting point, and solve it graphically? So you would need to get out some graph paper, or at least ruler and paper and angles and all that good stuff. And you're going to first start, here's where we're starting, and then put down, well, maybe that's going to be, if you're going to use 1 centimeter to equal 100 kilometers, that would be 7 centimeters long. And then they go south, they go straight south, 600. So that'd be 6 centimeters. So if we did that, 7 centimeters, 6 centimeters, we'd do this on graph paper, or maybe it's just 7 squares, or 6 squares. And then we go across here, and that's going to be 3 centimeters. And then they go north, and that's 4 centimeters. And they want to know, well, what is the resultant? And you would now graph that line, draw that line, and measure that. And you would measure how far that is compared to all these other ones. So if these were centimeters, you would have to actually measure that, and maybe you would find that that's 4.5 centimeters, which for us would come down to 450 kilometers. But you need to do that with a ruler and some graph paper, and if you wanted to figure out the angle, you'd actually have to use a protractor to figure that out. All right, let's do one more. Ralph is mowing the backyard with a push mower that he pushes downward with a force of 20 newtons at an angle of 30 degrees to the horizontal. What are the horizontal and vertical components of the force? So here's Ralph. He's right here. He's out mowing, and he's got kind of a strange leg there. Okay, he's mowing. And the handle for the lawnmower goes down this way. He applies a force of 20 newtons to that. And notice that when he's pushing on that, part of that is pushing forward, but part of it's pushing it into the ground. And that's true anytime you do something at an angle like that. You're going to have some of it where you're pushing it down into the ground. And so if this is a 30-degree angle, we want to figure out, well, what's my horizontal component? What's my vertical component? Well, that's pretty easy stuff as far as trig goes. It's pretty straightforward. So if we've got this angle, we want to figure out the side next to it, and we've got the hypotenuse. We're going to use cosine. So cosine is adjacent over hypotenuse. Adjacent is f of x, fx, and hypotenuse is 20. So just plug that, the information in. We actually don't know fx. We're going to solve for that. So we're going to put in our force of 20, cosine of 30 degrees, and you would end up with 17.3. If we want to figure out the other one, well, if this one was cosine, well, this one's going to be sine. So we're going to go and figure it out with sine. So same kind of thing, same formula. Plug in 20, sine of 30, you end up with 10. So he's applying a force of 20 newtons to that lawnmower. 17.3 gets that lawnmower to move across the yard. 10 is actually forcing the lawnmower down into the ground, making it actually harder to move because you're creating more friction. All right, I believe you are ready to do your practice problems.